Hello world, my name is IDW, and today I'm going to be going over this right here, which is a fairly basic ALU. It's a really nice ALU because it's fairly simple to build, it's really easy to implement into a CPU, it's really small, and it's not really that aggressive of a thing, like a CLE adder, for instance. So basically what I have right here is I'm going to first of all prove that it is actually an ALU, and then I'm going to show you how to build it. So as you can see right here, I'm doing a pretty standard addition problem, 5 plus 3. This is a binary 5, 1, 0, 1, and then the other one is a binary 3, 1, 1. So yeah, so other than that, this is just addition. As you can see, it's getting 8. It also has flood carry and cut carry, and if you invert the inputs, you can manage to get this up to, I think you can do any logic gate. But with just these two in the setup that I have right here, I can just do cut carry, which should make it so that it's just the NOR gate getting inverted, which would mean that it is an OR gate. Yep. So since this is actually a truth table, I can also really easily prove that this is, in fact, these logic gates are real, because these are all the different possible inputs that you can have to the adder. And while we're on cut carry, you can't have anything come from this bit to this bit, so yeah. So the only case that it can be off is if both of your inputs are off. Otherwise, in any other situation, it will be on. The other command that I have is flood carry, of course. That would be just XNOR. That is, if there is one input on, then the output is off. Otherwise, it is always on. That's pretty much... There's a lot of ways to define XNOR, but that's the one I like to go by. So, yeah. As you can see, that is an XNOR. Now, if we do this, then the actual thing that it's going to result in is a NOR gate, which is basically the opposite of an OR gate, since the flood carry acts like an inverter if you have the cut carry active. Ooh, that doesn't... Wait, does that? It doesn't actually matter. I can just add a repeater there. Anyways. So, yeah. Those are all the functions that you can perform at a basic level. You can also do carry in, of course, and 8 plus 1 is 9. So yeah, that's just about it for showing this thing off. Alright, so now we're going to actually be building this thing, and there's a thing that I forgot to add in the last recording, and that is that I'm actually, in this version, going to be adding on the actual inverter, well, the input inverters. I forgot to really mention those in depth. So, yeah. So, the thing that initially made me actually try to build this, originally build this design, was that I wanted to have an adder that had its inputs arranged in AB, AB, AB manner, like a normal, what's it called, ripple carry adder. The annoying thing with Atomi's XOR-based ripple carry adder design, sorry, instant carry adder, technically, is that normally you'd have your inputs like this, but you have to have them in a slightly more annoying for memory configuration. So yeah, that's why I'm actually going to be building them in this format rather than that one. So anyways, so now I'm going to take power from this AND gate down here. By the way, the reason that I've done this is I need a NOR gate and an AND gate in order to make a actual XNOR gate, which I'm going to be using as the half adder in this. So then what I'm going to do, oh yes, and also slab so that a whole bunch of stuff doesn't conflict. But yeah, anyways, so now I have managed to OR these together, so this data right here should, if I've done everything correctly, act as an XNOR. So sure enough, one input on, it's off, both inputs on, it's on, and the other input on, it's off. So yeah, we have made ourselves an XNOR. So I've, however, have also kept the AND gate because I'm going to need that to actually build the carry line, because the carry line needs to generate a signal. Well, the carry line needs to have some way to generate a signal anyways. I'm going to do that using a repeater just because I don't want the signal to conflict with this right here, and I need it to come from this AND gate. Also, when I actually build the flood carry, it's going to be right here, so it's going to flow backward into the first half adder, and then it will just conflict with all sorts of things, which I don't want to happen. So that's why I'm not doing that. Anyways, this is an instant carry adder, as I've hinted at before. So yeah. So what I'm going to do is I'm going to put a piston here to accelerate the carry. That's how an instant carry adder works, and I can't place pistons. So then I can just bring that up like that, and I have the ability to propagate a addition sequence over. So yeah, this is basically the first half adder that I am going to end up built. So for the second half adder, I'm just going to be using the Tommy's, no, not the Tommy's XNOR, a multiplexer based XNOR. And the reason that I'm going to be doing that is I can actually do a bit of a swivel with it to save space in this direction. Also, the original signal is going to be coming from here, and the piston that I'm actually going to be using to power this multiplexer-based one is going to come from right here. And since I've already had to move the signal up to there in order to make it so that this piston extends, it's going to just be a little more handy. So that's that. Come on, Redstone, get placed. And there we go. So now we should theoretically have a full adder. So 0 plus 1, 1, 1 plus 1, 2, and 1 plus 0, 1. So excellent. Now we have to test to see if the carry line actually works, if it can actually carry in. So 1 plus 0 plus 0 is 1. 1 plus 1 plus 0 should be 2. 1 plus 1 plus 1 should be 3. And that should be 2. That should be 1. And that should be 1. So yeah, I didn't show you that on all of those, but anyways, that's how the actual, so yeah, it's a working adder. So now all we need to do is stack it, and then we can move on to building the flood carry and cut carry, and all the other functions that we're going to use in an ALU. So that's there. So now, okay, so there we go. So now the first thing that I'm going to be building is the flood carry, because I've sort of already explained that I'm going to flood the carry through this line here. So yeah, that's exactly what I'm going to do. And I can just do that. So basically what this one is going to do is, now it's just going to flood the carry, and I think I've explained what that does. It makes it so that it's into an XNOR, and if you're using any other logic gate, then it's going to invert it. So like NOR gate, like what we're going to do with cut carry, it'll turn it into, no, it'll make an OR gate into a NOR gate, yeah. So now the next one's pretty easy to implement. It's the carry in. So all I'm going to do for this is I'm just going to do this. And the reason that I'm going to do this is the flood carry actually needs to affect the first bit, which it won't because this is where the flood carry, this XNOR is where the flood carry would normally affect it. So I do need to OR it in with that in order to make it perfectly work well. But anyways, now, as I said, actually I don't think I've said this yet, but the nice thing about this design is that you can actually, well, you can use, you can actually, well, basically all of the inputs for this are all lined up, which is really nice. You can, you can make opcodes really easily with it. Unfortunately, that doesn't actually apply to the carry-in. But anyways, of course I can't fly. Now I need to just power these blocks right here with this. And you know what? Sure, I will do this line off camera. Anyways, so now we're going to actually build the input inverters, which can be any XNOR you want, or XOR, depending on what you want. But I'm just going to use this XNOR right here, which is the multiplexer-based one, because it's simple, and I'm running out of time. So, yeah, not much to say about this. Actually, I didn't really explain how it worked, but I'll put that out in another video. And of course, I forgot to make that into a slab. Not much I can really say about this. I've already built the XNOR and yeah. So now all I really need to do is just stack this thing. Yeah, not much to talk about. Oh, make sure that you use slabs on alternating pistons. That's why I'm actually using different redstone lines, because since every other input is going to be a different input into the adder, you're going to want to make sure that it's actually, well, it's inverting the right thing. Because if I was to have both of these off, then, well, if I was to have them on the same wire, then I would be inverting all the inputs, and for subtraction, you only need to invert one input at a time. In most cases, yeah, in all cases, if you want to be really weird, then I guess you could. But, anyways. Stack 3. And also you need to invert these since they are technically XNORs and not XORs. But other than that, that's basically it. If you want to see subtraction, because I didn't show it earlier, let's invert this input. So that means that this input right here is inverted. So this is the negative. This needs to be the negative one. So -3 plus, guess what? 1, 0, 1, 5. 5 minus 3. And of course we have to carry in also because it's using 2's complement right here. You can't do 1's complement with this. We get 2. And yeah, and since that's on, it's positive 2. So